Bismillahirrahmanirrahim. Welcome to this week's class of digital communication. I am your course instructor Dr. Naveed Mufti at the Department of Telecommunication Engineering, University of Engineering and Technology, Mardan. So last week basically we started looking at what is bit rate, how we can determine it, and then what is the maximum pulse transmission rate that can be supported, and how multi-level pulse transmission can basically increase my bit rate. And we arrived at a general formula which seemed to coincide with the Nyquist channel capacity theorem for noiseless channels. And then we started looking at how data rate or bit rate is related to bandwidth, and how data rates can be increased without affecting the bandwidth by increasing the spectral efficiency. And we looked at the ways we can increase the data rate. After this discussion on bits, bit rates, data rates, bandwidth, etc., we then moved on to the PCM waveforms. We discussed their principle of working and construction, and we discussed 12 waveforms, and then we went through the factors among which we can compare those different PCM waveforms. Thereafter, we discussed the implications involved in memory communications, its advantages and disadvantages, and some practical applications of amplitude and phase, M level representations and modulations. After that, we introduced ourselves to the second major block of a digital communication system, which is channel encoding. And we discussed that generally channel coding falls under two categories: waveform coding, whereby we change the waveform of the signal, and structure sequence, whereby we improve the sequence of the message by introducing more redundant bits which are used for error detection or correction. So this week we will be starting off by looking at error detection. So first of all, we will discuss the schemes of automatic retransmission query. Then we will look at some very easy single and two alphabet error examples, and a code and decode paragraph. After that, we will discuss the types of error detection and correction codes. There are two main categories. We will go through some terms that we need to be familiar with when we are studying channel coding. And after this initial background, then we will start looking at some error detection codes, in which we will discuss single parity system, the BCC system, and the CRC system. As part of learning outcomes, at the end of this lecture this week, the students should be able to compare the performance of different ARQ schemes, interpret coding terminology, and explain the working of different error detection schemes. So now our discussion continues on to the next block within a digital communication system, which is that of channel encoder. So now we are moving on from this block to the next block, which is channel encoder. And channel encoder, decoder, collectively they are called channel coding. And the main purpose of channel coding block inside a digital communication system is to combat channel effects. So that is why the name is channel coding. So when the signal will pass through the channel, it will have undesirable effects. It can get affected by noise, it can be distorted, it can be interfered by other external signals, and so on. So all the impairments that might be encountered when the signal goes through the channel. So this is the way to combat all those effects. So we are preparing or conditioning our signal to better withstand the ill effects of the channel. So how do we do it? By adding redundancy. So we add some extra bits in this part of the process. So here in channel encoder, basically we add a few extra bits, and the purpose of those bits is to help us in error detection or error correction, or both. So adding these extra bits, which is called redundancy, so adding this redundancy, it implies the need for increased transmission bandwidth. Obviously now we have more number of bits to send, and if we want to send them in the same amount of time, so we have to send all those bits if in the same amount of time, then we need a greater bandwidth. So adding this redundancy, it increases our transmission bandwidth, or if we cannot increase our bandwidth, then it will increase our transmission time. And this basically, because channel coding is error control, so this error control is, it also adds complexity to the hardware design, which obviously becomes complex. So there has to be something in place, a hardware here and a hardware here, so that adds to the complication of the hardware design. Now, as I discussed earlier, there are two main categories of error control. Either we have error detection followed by retransmission, which is also called automatic repeat request, or we detect the error and then we correct it at the receiver. So we don't request for retransmission. So these are the two main categories of error control. The simpler error control mechanism is obviously this one. It has its plus and minuses, and the more complex is this, the forward error correction, abbreviated as FEC, which is obviously more complex because now this has to be smarter, your receiver has to be smarter. So when we come to those techniques or algorithms or schemes which only involve error detection and no correction, so when that is the case, there has to be a mean to inform the transmitter that an error has occurred at the receiver and that the retransmission is required. So in this technique, obviously the receiver is not making any attempt to correct the errors at its end, so it is requesting the transmitter to retransmit, repeat telecast. Okay, so all such procedures or means which are used for error detection only, and there has to be a means to inform the transmitter, they are called automatic repeat request, abbreviated as ARR, or automatic retransmission query, abbreviated as ARQ. So two names for the same thing. Okay, so now we come to the discussion of the different types of error control. So these are the ARQ techniques or ARR techniques, all of them which require the receiver to send some sort of message back to the transmitter if the transmission has been okay or not, and if it has not been okay, then the transmitter retransmits. So first of all, we start with the most basic of the three techniques. So this is the figure to illustrate that concept. This technique is called stop and wait ARQ, and in this technique, if you look at this figure, the transmitter sends a symbol. This can be a bit, this can be a block of bits. So these numbers actually, they can represent bits or they can represent blocks of bits. You can assume both. And the x-axis is the time axis. So for example, the transmitter, it sends a bit or a block of bits which get transmitted, and on a time axis they get received after a certain time delay, little bit of time delay. Once that bit of that block of bits or that single bit is received successfully, the receiver sends an acknowledgement. The acknowledgement is received by the transmitter, and then it transmits the second bit or the second block of bits, and when it sends that, then it is received and its acknowledgement is sent. And once the transmitter receives the acknowledgement, then it sends the next bit or the block. So in this scheme called stop and wait ARQ, the transmitter basically waits for the acknowledgement of each transmission. So as you can see, it is waiting for the acknowledgement of each transmission before sending the next transmission. So here in this case, for example, let's say when transmission 3 was made by the transmitter, the receiver, it noticed an error in this transmission number 3, so it sent a negative acknowledgement to the transmitter. When the transmitter received it, negative acknowledgement indicating that there was an error, so then it retransmitted the transmission number 3, as you can see here. that was retransmitted. So it got retransmitted, and once it had its positive acknowledgement, only then it transmitted the next block or bit, which is number 4. Same thing happened here. Number 5, when it was transmitted, there was an error, so the receiver detected an error, and then it sent a negative acknowledgement, and that is why the number 5 was repeated again. So there is a retransmission whenever there is a negative acknowledgement, and there is no retransmission when there is a positive acknowledgement. But in either case, there is a wait period where the transmitter is waiting for the acknowledgement before it transmits the next block or bit. So as you must have guessed, this would take a lot of time if it keeps waiting for the acknowledgement before it sends the next one. So for example, on time axis, if you see here, from this time here to this time here, no data is being transmitted or received, nothing is happening. So time is a precious resource, so a lot of time is being wasted. So then we can go one step ahead and we can improve this situation. So what we do is that now we have a continuous transmission. As you can see here, the transmitter basically is not waiting for any acknowledgement, so there is no time delay or time gap between the transmission of 2 blocks or 2 bits. So immediately when it is done with the first, it starts transmission of the second, and so on. So it is continuously transmitting here. So as you know, the sequence numbers have been assigned to each block of data. This is the sequence, yes, and it sends number 1, which obviously gets received after a time delay. If you notice on this figure, by the time the receiver has received number 1, the transmitter is actually transmitting block number 3. So it is not waiting for its acknowledgement. Anyways, so when the acknowledgement of the first block is sent by the receiver, by the time the transmitter receives it, it's a positive acknowledgement. By the time the transmitter receives it, it is already transmitting block number 5. So you can see that it is not waiting, it is continuously transmitting. It is not waiting for the acknowledgements. So this is the acknowledgement of block number 1, of block number 2, of block number 3, and this is the acknowledgement of block number 4. So let's say in block number 4 there was an error, so a negative acknowledgement was sent by the receiver to the transmitter. So by the time it received this negative acknowledgement, it was transmitting block number 8. So it transmits it, and then it looks at the negative acknowledgement, and because there are unique numbers attached to every sequence, so it has to keep a record of which block's acknowledgement is it. So it has already received 3 acknowledgements previously, so this is the acknowledgement for block number 4. So because block number 4's acknowledgement is negative, it retransmits 4, and in fact it retransmits every block from 4 onwards. So it retransmits, so it restarts from 4, you can say. So it starts sending 4, 5, 6, 7 once again. So it basically it pulls back the transmission and it retransmits the error message and all the subsequent messages. So the retransmission starts from the negative, the one with the negative acknowledgement, as you can see here. So once again, by the time, as you can see in this figure, there was an error in block number 7. By the time its negative acknowledgement was sent, it was transmitting number 11 block. So once it finishes with the number 11 block, it starts retransmission from block number 7 onwards. So this is continuous ARQ with pullback. This is the second technique. So obviously in terms of the utilization of the resource of time, this one is much better than that one. However, it can be improved even further. With a little bit of more intelligence, it can be improved further, as you can see here. So once again the transmission is continuous, no problem, as you saw here. So same scenario, it is not waiting for acknowledgement, so it is continuously transmitting the blocks. Let's say the same block, block number 4, had an error, So it sends a negative acknowledgement. By the time it receives negative acknowledgement of block number 4, it is already on block number 8. So it finishes with the block number 8's transmission and then resends that block whose negative acknowledgement was received, only that block. So it resends that block number 4 and then resumes or continues onwards from 8. So it has to be more smart. It has to keep record of how many blocks it has transmitted, how many acknowledgements it has received, and so it only retransmits the corrupted block, only that is repeated, and then it resumes its normal transmission. So after transmitting 4, yes, it continues on from 9, 10, 11, 12, so on. Okay, so by the time let's say there was an error in block number 11, so by the time this negative acknowledgement was sent, it was already transmitting block number 15. So once again, after it transmits 15, it only retransmits number 11, the block which had an error, the block whose negative acknowledgement was received, only retransmits then that one and then resumes its sequence. So it has to remember its sequence, it has to tag its sequence, it has to keep a record of its sequence. So it has to be smarter than the previous two cases, but that is the best one. So that is why it is called continuous ARQ with selective repeat. Yes, not every block is repeated, only the block which had an error, that is repeated. So these three are basically the types of different error control in place when we have only error detection. So these are error detection only techniques normally that are used in digital communication system. So now we are going to look at some error detection techniques, at how errors are detected. Okay, so we will start off very simple examples to build up that concept. So let's say this is the English word you have received or typed or seen. Do you think there is something wrong with it? Is there an error? Do you think there is any error? Where do you think is the error? And how many alphabets do you think are in error? So consider yourself as a receiver which has received this word, which is spelled as expensive. So it has received expensive, and you as a receiver are trying to guess if there is an error and where is an error and how many alphabets are in error. So using your current knowledge of English language, you are able to in your mind you are able to detect if it has an error or not. Okay, and the Microsoft Word itself, you see that if you type this word, it will underline it with the red color to tell you that there is something wrong, there is an error, and then it also allows you to correct it. If it's there in its dictionary, it guesses or it gives you some suggestions that it can probably be this word or that word. So try it in MS Word and see what options does it give to you. Anyway, so this word is in error and there is an error here. Now your receiver is smart. It can detect, Microsoft Word, that red underline, that is detection of error. And if you go to that word, if you right click, it gives you the suggestions, and if you pick one of the suggestions, that is the correction of an error. So here you will have an underline here to show that there is an error, and based on your current knowledge, I am sure you will be able to identify that this is the error, this K should not be here. So there is an error in one alphabet and this K should be replaced by X. Yes, so that is here. So your guess would probably be right, expensive. What about this one? If the same word had two alphabets in error, now what would you do if you were not sure what two these alphabets are, or if they are missing, or if they are corrupted, and you have to make a guess about it? So in your dictionary, in your English language, probably you have the word expensive. So that is what you will do. You will fill an X here and you will fill an E here, and you will try to make it the word expensive, assuming that that is what was sent. So actually you're trying to correct, you're doing error correction, okay, but I can tell you this is what was transmitted, this is what was transmitted, and whatever you substituted here, you probably ended up by a wrong error correction. Okay, so you might have detected an error, but when it goes to correction you might make a mistake, and that usually happens in digital communication. When the receiver goes into error correction, sometimes it makes the right decision, sometimes it doesn't make the right decision, so ends up with the wrong value or the wrong word in this case. So we started off with a very simple example that there is one error in one word and how we can detect it, and in this case we can also correct it, but if we cannot correct it, at least we can detect it, or Microsoft Word can detect it. How about this one? Are you able to read what is written here? I leave it to you as a home reading assignment, that you go through it, and by the time you reach the end of this passage you will know what we are talking about, that the human mind, your mind is basically a very smart receiver which has inbuilt error detection and correction algorithms. So not only you are able to detect errors, you are also able to correct them, at least mentally. You will pronounce the right words in this passage, even with the errors you will be able to. So in terms of vocals speaking, you are already correcting. When it comes to writing, then it will take some time, but you can also then correct the spelling as well. So I leave it as an exercise to you to go through this one. Make sure you do, it's very interesting. If you are successfully able to read the whole passage, you will find out that that's an interesting research and interesting concept. Okay, so error detection or correction techniques, they mainly fall under two categories. Either they are block based or they fall under the category known as convolutional. So channel coding either happens in the form of blocks, so called block coding, or in another form called convolutional coding. So the difference between these two, the block coding and the convolutional coding, is the presence or the absence of memory, or in other words storage registers in the encoder. So in convolutional encoding you have storage or registers or memory inside the encoder, whereas in block coding there is no such storage of previous data or previous bits inside the encoder. So that's a fundamental difference between these two approaches for error detection or correction. Block codes or convolutional codes, the two main categories. So there are a few terminologies that you should be familiar with when it comes to talking about codes. Yes, coding terminologies, they will be very useful. Some of them you might have studied and some of them you may not have studied. Anyways, so redundancy, the first term is redundancy. So you know, I discussed this in the introduction of channel coding, that we add some extra bits either for error detection or for error correction. We add some extra bits to the data bits. So those extra bits which are added, they are called redundant bits or parity bits or check bits, whereas the original bits that represent your message or information, they are known as message bits or data bits or information bits. So the bits that you have, normally they are either of this category or of this category. Okay, so with a selected number of message bits, we will add a few data bits, we'll add a few redundant bits. And redundancy is basically the ratio of parity bits to data bits. So the number of extra bits you add divided by the number of data bits, this ratio is called redundancy. Sometimes it is expressed as a percentage, so we multiply that by 100. So the notations we use is that our message bits or data bits, normally they get indicated by k, small k, okay, and the number of data bits and the extra bits that we add, when they are combined, we indicate the combined number of bits by n, small n. Okay, so this term code bits or channel symbols, this refers to the combination of data bits and parity bits. So once all the bits are combined together, then they are called code bits or channel symbols. So basically channel symbols or code bits, they are the collection of message bits and parity bits. So code bits are nothing but combination of data bits and parity bits. But because now they are combined into one unit, they are not data bits only, they are not parity bits only. So that is why we give them another name. We call them coding bits or code bits or channel symbols. So as I said, if we have n code bits, so among those n code bits, k bits will be data bits. So the remaining number of bits are parity bits or redundant bits. So n minus k. N minus k is basically the notation used for the number of redundant bits or parity bits or check bits. Okay, so in coding terminology we use nk. We use nk. So the word nk or the term nk, that refers to the fact that we will have the total number of bits as n, among them k will be data bits. So n minus k will be the number of redundant bits or parity bits. So in that respect, coming back to our definition of redundancy, which is defined as the ratio of parity bits to data bits. So based on these values, the value of redundancy is basically equal to n minus k, which is the number of parity bits, so divided by k, which is the number of data bits. So this is redundancy, and as I said, sometimes it gets multiplied by 100 if we want to express the redundancy as a percentage. And the next terminology is coding rate or code rate. That is basically the ratio of data bits to total bits. So the ratio of data bits to total bits, it is represented by small r, and based on this terminology, what will be it equal to? It will be equal to the ratio of data bits k to the number of total bits, which is small n. So this is coding rate, and as you can guess, coding rate or small r, that will be between 0 and 1. Okay, so now we come over to the last two terms, code word and data word. First I will discuss data word. So when a certain number of message bits are grouped together, that is called a data word. So for example, if our system has decided that we will deal with a group of 4 data bits at a time, so those 4 data bits together, that is called a data word. So a data word is basically a block or a collection of data bits, whereas a code word is longer than data word, and code word is basically a block or a collection of coding bits or code bits. So a code word is longer than data word because a code word also contains, in addition to data bits, it also contains parity bits. So these are all different terminologies that you need to keep in mind as we go on to discuss the different techniques of error control, error detection and correction. So first of all, we will be looking at the different types of block channel codes or block channel coding techniques. So normally we discuss these 4 categories. Some of them might be a repetition because they are so simple that you might have studied them elsewhere in your courses in the undergrad. Anyways, so we have the simplest form of block channel code is that of single parity, and we can also have block parity, or better known as BCC. Then we have the cyclic redundancy checksum, CRC, and finally we will be looking at Hamming code.